As mentioned on slide, I'm a research engineer at Google DeepMind, and I work on the language model interpretability team. So essentially, that's doing mechanistic interpretability research, as the title of the talk suggests. And this is a field I hope you're all familiar with. So I'll be kind of like glossing over the introduction fairly quickly, but feel free to obviously just Google mechanistic interpretability or the papers that I mention if it's unclear, and also have a low bar for answering questions, both in chat or interrupting. I will probably send some questions to be answered at the end of the talk when I'm more happy to answer a general questions, but especially if it's a clarification question, I think you said the wrong thing, or what do you mean, what did you say at that point? More than happy for you to just put something in chat and I'll try and monitor that or interrupt. And yeah, my talk will be maybe into 3 sections. I'll give a very short introduction outside of these 3 sections on my background and how I got into this field of mechanistic interpretability. And then maybe the 3 sections of the main talk will be giving a brief kind of deep dive into the IOI and AC/DC papers. And don't worry if that's kind of just jargon for the moment. We will go through those in the coming slides. And my guess was that you probably had some familiarity with the IOI work. This was I'll scroll forward to this diagram here. You might have seen before of a circuit. So I'll be very brief on that, but maybe some work that I led last year was on this kind of automated way of doing this circuit finding. And since I led that work, I might have some more stuff to say there about how I kind of picked out that project and why I thought that was an important kind of project in the kind of mechanistic interpretability space. And then, yeah, it's maybe a second section of the kind of whole talk. I'll give a brief summary of the kind of current mechanistic interpretability research we're doing at DeepMind, so abbreviated to MechInterp, since this is a bit of a mouthful. But hopefully this will give some kind of sense of what the team that I work on is doing. And we've also released a bunch of research publicly, as well as kind of open sourced tons of useful sparse autoencoders, which we'll explain in that section. And so I think this is particularly relevant to people both inside DeepMind, obviously, but also outside that as well. Yeah, if possible, I think everyone could mute themselves. There's 1 or 2 people who are still unmuted. Thanks for the ping in chat. And yeah, then the kind of third section will be kind of advice on kind of the field and doing machine learning research in general, and kind of looking forward about what kind of future research that both that I'm interested in doing personally, and I think is important for moving the kind of field forward. And yeah, okay, so let's start with kind of my background in brief. So I was a maths undergrad, and I was pretty interested in AI safety, as well as kind of how fast machine learning was moving in about 2021 and 2022. And I'd done some small scale projects, like a research paper while in undergrad, but really I started doing much more kind of interpretability research when I did a program called MLab, which I have a screenshot, which is online now, but it's kind of discontinued. And you can think of it as very similar to Arena actually, but it was on in January 2022, so a few years back. And that was where I really got into actually getting the activations inside of models and interpreting what was going on with them, and that really kind of hooked me. I really enjoyed that research process, and yeah, since then I've really kind of tried to do a kind of diverse set of research projects in the kind of interpretability field, because I think it's been somewhere where lots of progress has been made, and we didn't have much progress before a few years back. And yeah, that's kind of where I got into interp. And then beyond just going on and learning what interp was, I kind of wrote papers while at a company called Redwood Research, and the screenshot stays on screen because they're the same kind of company that sponsored that kind of introduction to machine learning and machine learning engineering for interpretability. And we wrote the paper kind of IOI, or this is the interpretability in the wild paper I briefly referenced, but I'll go into that later. And yeah, began working there for 6 months. Unfortunately, they kind of pivoted away from interpretability, and so I wasn't working there after some time, but after that point, this is 2023, I got working with Neil Nanda, who I would highly recommend if you don't know the name already, because he has a fantastic website with tons of stuff on pretty much everything interpretability related, whether that be a quick start guide to how to do interpretability research, as well as a reading list of kind of some of the important papers in the field. And yeah, Neil is great, and I worked with him during a program called MATS, which there's a link here for. And funny enough, I now like actually mentor formats. So I'm like one of the people who will kind of take on some kind of like researchers, and we've put out like loads of research both with Neil, and there'll be some upcoming papers that I'll be putting out as well in the kind of interpretability space. And yeah, I think this is like a good program and maybe useful in this kind of introduction to how I got into this stuff, because this is kind of going beyond just kind of like tutorials on like how to do research, but actually kind of like executing on projects. And yeah, like I like most of my external collaborations go through the MATS program, as well as some kind of joint collaborations with Neil. I think like some really like awesome work has come out there. And I think we'll discuss more of this in like kind of like the looking forward part of the talk. But yeah, that's kind of like all the kind of like introduction. So yeah, onto like kind of the main section about like maybe a deep dive into a paper. And so yeah, the paper being discussed will be this paper called the AC/DC paper, or automated circuit discovery. But I just skipped over a slide because I do want to give a brief one slide summary of the kind of like prior work to AC/DC, which is this interpretability in the wild paper. So apologies for the excessive number of names here, but this is like either known as interpretability in the wild or the IOI paper. This is because it's all about this task, and I know some of you are familiar with this, so I'm not going to dwell on this too long, don't worry, where we have a bunch of sentences of the form, like when Mary and John went to the store, John gave a drink to, and then clearly the correct completion is Mary, but like this is somewhat surprising as a capability for like a very dumb language model, because if you just kind of predict the most common name in the sentence, the most common name is John, and so this is a task where we define success as kind of the model predicting the answer Mary rather than predicting the answer John. And indeed, some like very dumb language models like GPT-2 Small can perform this task. And the whole paper was about interpreting like exactly how on like a component by component level this kind of task worked. And yeah, I hope that maybe you have some familiarity with that. There's a bunch of like maybe Neil Nanda tutorials, and it will be covered in like the arena work as well. So apologies for being brief, but I think that's the kind of only the high level kind of understanding you need to have about what that paper is. And this brings us on to automated circuit discovery. So yeah, I think the motivation for this work was that like I'd really enjoyed kind of contributing to the kind of like IOI paperwork. I thought it was kind of exciting that like there hadn't been very many papers before that had really done that kind of like deep dive into just like some tasks to understand from end to end how the language model carried it out. And I think there's a common thing with kind of like machine learning research where like you have some early progress which is kind of laborious or has many steps, and then later on we find ways to kind of automate that or simplify it. And the kind of like automation part is really where things maybe like accelerate further. And so my take was that like it was somewhat important to try and find ways to kind of automate the kind of process we were doing in a paper like interpretability in the wild, because like it is just like really like long-winded in terms of researcher time to do like lots of like manual experiments. I think sometimes it's very important to, and you can learn a lot, but it's like a lot of like time to do that kind of work. So the idea behind AC/DC was to take our like main kind of like methods we were using to determine which parts of the circuit are which parts of the model, I say, are in the circuit, to take those kind of like techniques and then to use that to like automatically find what exactly the kind of outline of the circuit was in like a automated fashion, just with a simple algorithm. And yeah, I want to kind of like maybe make a key point here that this is not just like that everything's done. We're like we can stop doing any manual interpretability now. That's kind of not the pitch for this project. It's kind of more like an early stage step to like figure out whether this stuff is possible and like what the kind of like challenges are if we want to continue doing this work. And so a key thing that's not done with like a paper like this is we don't say like what the kind of different components are doing. So we have a label diagram here where we have like, let's say like attention head in layer 10 and index 10, but we're not saying exactly what that head is doing. It's just like one node in a big causal graph. And as you might have noticed, and if you know the paper, you'll also be familiar with, we want to have labels on these nodes. Like we want to say that like I think it's 10.10 is a backup name over head. We want to give some like semantic description of like what part of the algorithm that kind of like attention head is implementing. And I think this problem, for what it's worth, has also been attacked by a bunch of other papers. So there's for example, a kind of exciting OpenAI paper, which was I think from 2023, when they got GPT-4 to label a bunch of the neurons in GPT-2. So that's a paper paper called like Language Models Can Explain Neurons in Language Models, as far as I remember. And so I bring that up because I think this kind of like AC/DC work is kind of just finding like the structure, like which parts of the model matter for a given task. But that's not just kind of the end of the story for kind of like automating like mechanistic interpretability. We also need to actually describe what these different like parts that matter like actually do. And there are also works that are like aimed at that question, as mentioned with the OpenAI work. So yeah, I said a bunch of things. Is there any maybe questions on that? Because that's probably a pretty like speedy introduction into kind of like what the kind of like high level thinking behind this paper is. Check the chat. Nope. Okay, cool. As mentioned, feel free to answer questions anytime. I may like push them back to later in the call, but please don't worry about that. I'll definitely keep them in mind and we'll be able to answer them later. So don't feel any pressure there. Cool. So moving on, let's to be more specific about what we're like doing when we're talking about kind of like automating circuit discovery. I think the key technique that we wanted to like zoom in on with like the AC/DC paper was this technique called activation patching, which was used in the kind of like IOI paper, but I think it's worth kind of pausing on for a moment because it's like really like quite a powerful technique which can do like many things in interpretability. And there's been a bunch of like follow-up work that's like done other stuff with activation patching too. So the core idea is that like if we want to kind of test some hypothesis about how how a component inside a language model works, then like an important thing we need to do there is do like a causal intervention. If we claim, for example, that like there's a pathway in the model through which the name Mary flows, then this suggests that like if we replace the kind of like the normal kind of activations when you run the model on the token Mary with some activations that come from a completely different prompt, such as like when David and John say stuff, then when we do this intervention, which is called activation patching, so taking activations from like a attention head or from like a path, like an edge, a connection between two parts of a model, we take that activation and we take it from a different prompt and like splice it into the forward pass of like a Mary and Bob sentence, then we would expect, given the hypothesis as mentioned was that there's a path carrying the word Mary, that like the performance of the model will like decrease, it will break the model in some way. And you can also imagine experiments where if we would claim that like this path was about like a name is being kind of like transported from like the earlier part of the path to the later part of the path, but it's like just the fact that there's a name, it's nothing more specific than that, well then this kind of like David activation would be completely valid. That's like also a name or whatever. So in that case, when we did this kind of activation patching experiment, we'd expect nothing to change. And so this is like one of the key tools we have in just mechanistic interpretability in like full generality to like actually test our hypotheses. And this gives us like a big advantage over kind of like other fields of science, like in neuroscience, for example, where it's really hard to have this kind of like read access and write access to like the kind of systems we're studying, where we're unusually lucky that like all you need is a little bit of infrastructure on top of like basically any kind of machine learning library, and it should be possible to actually get out what the activations are inside a model and then put them back in. And like I'm sure you probably worked with, there's a library called Transformer Lens, which is again another one which has made by Neil Nanda and has a ton of tutorials attached to it, is a good kind of like library that is basically at its core adding that kind of functionalities to like Hugging Face transformers, effectively the ability to have this kind of read access here to take this David and John style activation, and then also have the write access to push it into like the forward pass of Mary and Bob. And yeah, so why are we talking about this in the context of automated circuit discovery? Well, the idea is, so long as you've kind of decided upon some data sets, like a data set of, I don't know, David and John and names like this, versus a data set of names such as Mary and Bob, then you can automate the process of activation patching, doing it across like kind of all like edges in the model. And there's a little bit more nuance to not just search through like the huge set of edges that are present in the model, but the method essentially boils down to finding the important edges in the model such that like when those are removed, this will break the model, and therefore keeping those edges in the kind of like circuit subgraph that AC/DC finds, while also kind of removing all the like edges that were kind of irrelevant for the model's predictions, and then getting this kind of like high-level structure of like what the kind of like circuit that performs this task looks like. And yeah, that's the kind of like motivation for activation patching. And then I think I also mentioned this because I'd recommend there's a bunch of follow-up work on a technique with a very similar name, but called attribution patching. So I think I don't have sharing access to a different tab, but yeah, I think maybe I'll just put it in chat. So I would recommend looking into, as like an extension thing, attribution patching. Yep, as put in chat. Yeah, spelled right. And this is a method for doing this kind of like activation patching approach, but like making it like an approximate method. So not exactly calculating what the change is when you like splice in activations from one input to another, but instead like approximating what the effect would be. And the reason why approximation is a good thing is because it can be like a lot faster than the activation patching workflow, and therefore has been like pretty beneficial for a bunch of follow-up research because it's significantly speedier. And yet, like surprisingly, despite being like an approximation, which is just like pretty simple, it doesn't seem to lead to that much degradation in performance. And so that's kind of exciting follow-up work that also came from this kind of activation patching idea. And to be clear, maybe I'll be a bit clearer. All of this research, like automated circuit discovery and interpreting in the wild, does build on a ton of kind of existing research in like NLP, as well as in kind of like interpretability in general. Like, for example, there's like a Rome paper which did this, and there was a paper called causal mediation analysis, and I just name drop them because a lot of people have also had this similar observation that like doing these kind of patching experiments is super important, and they all choose slightly different notations and setups and stuff like that. And I think that like I don't think it was called activation patching before this kind of like IOI work, but like this is not like a completely original idea which we just came up with one day. It's kind of like something which has been in the air for a while, I suppose, and I think that it's become much more popular since kind of these works, but I don't want to claim credit for something that's not like kind of like what I've like created or whatever. It's more just like I think it's worth like zooming in on because it's like a really like powerful technique, let's put it that way. Yeah, and with that being said, maybe I'll check chat again because I am going to be moving on to kind of like the current work that we're doing at DeepMind, at least in mechanistic interpretability on sparse autoencoders. I don't know if anyone has stuff in chat. Oh, awesome, thanks, Akangsha, for the link. And yeah, so moving on to maybe the next section of the talk, I'll be briefly discussing kind of what sparse autoencoders are. So I mentioned kind of like past research that I'd done and like what the kind of motivation was there, and what I think are kind of like the key takeaways and like things that have aged well from that research. And now a lot of the work that we've done at like DeepMind in the past like 11 months while I've been working on stuff, as well as what we're kind of currently pushing on right now, is to do with this kind of tool that we're going to call a sparse autoencoder. And so maybe one method I could use to kind of motivate why you might care about like a sparse autoencoders is that you have in the IOI paper a very like exciting kind of like attention head level description of like how the circuit works. Namely, we have a bunch of like attention heads in various categories, and we can have like labels on the categories for what they represent. But like we had a difficult time understanding what exactly the MLP layers in the language model were doing. And so people traditionally think that the MLP layers are probably doing stuff like kind of transformations to each token, or maybe doing like storing the facts behind like the information that the language model can recall. It's a bit of a mystery, but whatever like they're doing, we don't really have a way to like kind of like get a good grip on them with the activation patching methods for reasons I'll get onto in a moment. And we see this problem again in the kind of like AC/DC circuits, where we're able to like look at MLP, as you can see these M5, M0, M1, etc. in this diagram here. But the problem we have is that we don't really get any deeper into like what exactly that MLP is doing. Often in an attention head, we can describe them, as mentioned here, as like induction heads and duplicate token heads, and give like an actual description about what the attention head is doing. But for MLPs, it's just kind of like, this is a middle node. It takes these inputs and it produces these outputs. We really have very little idea about what's going on inside there. And so this motivation for sparse autoencoders is going to break open the MLP and not have it just be like kind of either a blob in the circuit diagram. We're not really sure what's happening with that like kind of point. Or alternatively, it's just something that we might be able to get access to inside our circuits, which follow-up work has actually done in some cases, rather than just have just attention heads. Slide. Yeah, so I mentioned like we can't break up the MLPs, And what I mean by this is that the neurons inside MLPs, so there's like a large number of neurons inside, like just like after the activation function of the MLPs, you might hope that those just kind of correspond to the different kind of concepts that the model's like thinking about in some ways. And this would be very helpful because then we could just do interpretability on those and just like describe like both why a certain neuron like fired and then like what effect it has on like the later part of the network. That would be great if we could do that. But the problem is they're not generally interpretable. So what this means is, this is an example from vision models, for example, that we might have a neuron that like when we like optimize to find, well, what does this neuron fire on? It's kind of this massive mess with like cats and foxes and like car bonnets, if you can see here. And so we can't really give descriptions of like how models work if the kind of like variables in our description effectively are like, well, this part was a cat or a fox or a car bonnet. We don't really know which one, but it was one of those. And like, that's how the model works. It's like representing the cat or the dog or the like the car bonnets. Sorry, cat or fox or car bonnets. And so that's the problem. This is the jargon term for this is like polysemanticity. Like each neuron corresponds to more concepts than just one, effectively. And yeah, like there's something wrong here. Like our understanding is clearly off because this is just not very helpful as a way to understand the neural nets. And this motivation for sparse autoencoders is what Anthropic did. I think it was in late 2023 with a paper that was called Towards Monosemanticity. So I use that kind of like jargon heavy term for like polysemanticity and like many meanings to each neuron, but they tried to work towards what's called monosemanticity, which is where you would hope that you could take some activations where they're kind of polysemantic, we don't know what's happening, and then extract from those monosemantic different like concepts inside of the previously kind of polysemantic mess before that. And so this idea is basically the architecture of a sparse autoencoder. So the idea is we'll have some input activations to this one layer MLP, which is the sparse autoencoder. We'll then like learn a linear transformation to like see whether there like are like a larger number of like kind of concepts present in the model compared to like the number of like input dimensions to the sparse autoencoder. And then we will train this such that like when we take an activation function like a ReLU and then project back down with like the down layer of the MLP, then we like will train this such that it reconstructs the input. So this is the kind of autoencoder part that we're just learning like a neural net, which hopefully just reconstructs the input as its output. And that would be very boring on its own. Like that would be trivial. You could like, there are many functions you could learn that would do this kind of transformation and turn the inputs back into the reconstruction of the inputs on the output side. But the key thing the sparse autoencoder does is it enforces like a sparsity penalty on the kind of hidden layer here. So we train with like I think it's L1, like it's a standard kind of machine learning technique to try and incentivize there to be a very few number of these features in the middle firing. And the idea there is that like then we might have only like 20 or 100 at most kind of these like hidden layer like features active, and then we still might have a kind of a somewhat accurate reconstruction. That's at least the hope, but with only a few kind of concepts that are activated of the huge number in this like middle layer MLP. And this is a bunch of kind of like discussion and like theory behind like, well, here's an idea. It's a sparse autoencoder. This was already a technique in machine learning from before, like kind of like language models and the Anthropic paper. But let's just try this was essentially the approach that Anthropic took, and it worked surprisingly well. So they then, once they trained this with just kind of like a black box method, they'd look inside their kind of trained sparse autoencoder and look for like different features. And so to me, the most compelling like feature I remember seeing back in like 2023 was they looked for a feature and that it like rarely fired, but whenever it fired, it would be on these Arabic tokens. So you can see here, I don't know how well my Zoom will work, but yeah, definitely look up, I think I'll put in chat again. This is like a towards monosemanticity. I see a message as well, which I'll come back to in a moment. Apologies for the delay. So that's the kind of like a great kind of interactive blog post that Anthropic have on this technique. And they found that like kind of these individual hidden units inside the like sparse autoencoder correspond to like very interpretable things like this text is Arabic. And a question you might ask is, was any of this necessary? Like, was this actually just like a neuron? And they're like pretty certain that like this is not just like a single neuron inside the model, but this is like this Arabic feature is going to spread across many different neurons, because you can read off the weights, like what caused, if I go back to the previous slide, what caused, if this is say the Arabic feature, this Arabic feature to fire, which of the activations were relevant here, which the components were relevant, and it's a real mixture. Like there's like positive coefficients, negative coefficients, and it's really unclear like where exactly, which of the neurons effectively this kind of Arabic feature came from. And so their suspicion is that like actually the NLP layer was like computing far more kind of like concepts than it had as like hidden dimensions, and you required this kind of like second like kind of like layer sparse autoencoder, so like having a separate one layer like model outside of the network that would have like a larger number of activations in the middle, which could then actually extract these kind of like concepts which are spread across the inputs. So I said a bunch. I will go back to the question. I think Druv asks, are there any other techniques that might help uncover how MLPs contribute besides sparse autoencoders? Have you faced any challenges using them? Yeah, that's a great question. Yeah, I think that like it's good to like notice that like I've just like discussed one solution to kind of like the MLP problem, and it certainly isn't like the only one. Yeah, so it is not the case that like the neurons, like as mentioned here, are like never interpretable. I think I saw like a paper, even like, or sorry, a blog post, I think it was, even on like a language model, which showed there was like a single neuron which fired to distinguish between when a word was like a or an, like the two different forms of like saying like a dog versus an elephant or whatever. And so they seem to say that like that was pretty much what they thought that like the neuron was doing. Probably was doing a few other things, but it was pretty sharply mostly one thing. So sometimes you can hope that like the neurons, they just actually do have one concept. And like similarly for our sparse autoencoders, I give like kind of a rosy idealized picture where like the Arabic feature is like basically just fire in Arabic, and then like when it doesn't fire, it's kind of like English or like normal text. But like indeed some of the kind of sparse autoencoder features that we find, I think it's about 30% in our experiments, aren't really interpretable. We can't really understand what's happening. So there are definitely limitations of sparse autoencoders there. But yeah, I guess what other methods if you can't understand MLPs? I mean, there's I guess a ton of like more broader work in the interpretability space, which doesn't always require like the kind of like the researcher to really understand like exactly what like individual components of a model are doing. Like one example of this is there's a kind of a popular field called like activation steering, which is where you can kind of like add inside the middle of a forward pass, just the hidden state, doesn't really even like think about NLPs much. You can add some activation in there, and then like this will cause the model to have some like kind of property in its outputs. Like the model will start shouting at you in all caps or something like that. And this is kind of interesting because it shows that we can like use the internals of models to do stuff which like either kind of like was like very hard to get out of prompting, or even if prompting can already do it, then it's like a different way to get to the same end that prompting like got us to, which is interesting for thinking about like how the models work. And I bring this up as something different from sparse autoencoders to maybe like dispel maybe a kind of a myth, which I'm not sure if anyone actually believes, but there's a lot of excitement in sparse autoencoders after earlier this year Anthropic released a demo, which is great, with like a Golden Gate Claude model where they've activated some kind of like sparse autoencoder feature. I think it was like 10x or 20x the like normal value of that feature, and then the model like thought it was the Golden Gate Bridge, and it was pretty entertaining, and I enjoyed talking about it, or like playing with it rather. But I think that that's just like one method you can use to like add some activations into a model and steer it towards some outcome. And Anthropic weren't the first to try that technique. They were definitely the first to try it in like a production model setting. But there's been a ton of work both like before that and since, and will probably come out soon, that can show methods of kind of steering models by like adding activations into their internals that doesn't really ever think about like, can we interpret what this kind of like activation is doing or whatever, and yet can still kind of like deliver results and make the model do something rather than something else. So yeah, I guess to zoom out slightly, what I'm saying there is that like I'm probably mostly talking about stuff that's trying to understand at like a low level how these models are working, but like there's a bunch of kind of related work as well that doesn't really need to go that low level and can still kind of do interesting research there. And so that's another reason why you might not care as much about the SAE. Druv. Cool. And then where were we at? Yeah, so I discussed maybe a bunch of Anthropic's background and the kind of motivation for this stuff. But what have we been doing at GDM? Well, I think it's like a few months back now, we released what we called a GemmaScope. And we have a kind of a demo GIF here of GemmaScope, as well as maybe like the huge kind of like set of like files that are on Hugging Face right now. And again, you can search GemmaScope. There are a bunch of links to land on. And GemmaScope is the biggest suite of sparse autoencoders that exists, I guess, publicly and open source. And this was for like the Gemma 2 open source language models. So you can think of these a little bit like Llama, which is like obviously the most famous kind of open source language model, but Google's kind of version of Llama, where we open source them for like all of the layers of Gemma 2 2B, as well as all of the layers of Gemma 2 9B. And we also have a few like extra sparse autoencoders for models such as the 27B like Gemma model, as well as I think it's like there's a few for like the instruction tuned versions of the 2B and 9B. But a bunch of other details on these extra SAEs in our kind of like paper on archive for GemmaScope. And yeah, this is, as mentioned, why I thought it was worth discussing the kind of things that we're interested in at GDM, because we've been like lucky to be able to like use a ton of kind of compute to train loads and loads of sparse autoencoders that we're kind of excited about more researchers using, because while we think that like this technique is pretty promising, and we think this is one of the best, or probably the best way we found of like actually understanding what the internals of models are like doing by like labeling the kind of like different features present in them. While we think that's probably true, we haven't seen too many applications of like the SAEs yet. There have been a few papers on this kind of stuff, but like there are many like facts about models that we don't know how they work, and many kind of like safety problems that like can be addressed when you have a better understanding of like what the models are doing. And so we're pretty excited about that kind of work there. And yeah, I guess quickly check chat, because I think we're going to be moving on to kind of like future work and what we're interested in at GDM past kind of GemmaScope and work like that. I will also, in case you just want to have like a skim of like why GemmaScope is kind of a cool tool. We worked in an external group called Neuronpedia. So this is a researcher called Joseph Bloom, and the main engineer behind that was Johnny Lin, and they're great and built like a whole kind of like steerable interface for interacting with models when you have kind of sparse autoencoder features, as well as ways to kind of see which SAE features are firing on different prompts. But yeah, as I move on, before I move on maybe to the next section, there's a question from Eunice. I'm wondering, would make the SE variational help with interpretability, because it enforce some regularity in the space of the hidden layer, the same ways that VNAEs enable interpolation when it's harder with normal AEs? How, by variational, you mean like you pick some like variational lower bound for like the loss term, Eunice? Could you clarify if that's all right? Feel free to unmute as well if you want to as well, but you can also type in chat.
Yeah, sorry. Yeah, I meant yeah, exactly the same way as so for example, you could have a penalty to like add some sort of regularization, right? Like you would want a multi-dimensional Gaussian, for example, in the hidden space. So I was wondering, like, if you if you impose this kind of regularity in the latent space of the hidden layer, it helps decoupling the features. Because
yeah, that's a good question.
for these autoencoders, you end up with a space that's very badly structured.
Yeah, that's a good point. So that kind of, as far as I understand, the kind of like the question asked was, should we impose some more constraints on the kind of activations of the hidden layer of the autoencoder, or like some like other kind of like different architecture for this kind of like problem discussed here, such as kind of we could like try to train this such that like the hidden layer activations are roughly like multi-dimensional Gaussian. Do contradict me, Eunice, if I
Exactly.
cool. Yeah. So I guess there's some reasons why this is like quite an interesting thing to do and has some like useful applications, but I do want to like give some like maybe limitations of why that's not maybe like the immediate thing that like we would want to be working on with SAEs. So the reason why this is maybe kind of interesting and a good thing is a bunch of kind of like these variational style approaches have been used in models, especially vision models, like as you mentioned, VAEs and GANs, And they've allowed people to do this kind of activation steering work like long ago, where you probably have seen pictures where you can like steer a man to smile or to like to frown based on a single direction inside like a GAN, I think it is. And so, yeah, by looking at like, I think it's, I don't know the exact reference, but if you would like search for something like GANs, like frowning man activation space or something. I'm apologies, not going to search that up now, but I might pass it on to Akanksha and we'll share after the meeting. But that's very interesting to me because that's an example of this kind of like linear representation inside like neural networks, which way predates kind of language models and all the kind of stuff with linear representations we discussed here by like a long way. And so it's pretty interesting that there are like some linear representations in models when, as Eunice kind of suggested, you train with kind of different objectives on the hidden layer. I guess the reason why we probably wouldn't like have a Gaussian kind of like prior, let's say, on these kind of hidden layer here is that I think what we're trying to do with the sparse autoencoder is like extract the variables that the model's using at a given place in the language model. And so when I like speak a sentence like, let's say, the dog ran up kind of like angrily to the house or something, then like I'm conjuring up some concepts like dogs and anger, maybe it's a story or whatever, and there are some kind of active concepts when I say some random sentence like the dog runs angry up to the house. It's also in English. Maybe I formatted it with like correct text rather than typos or whatever. There are some facts about each sentence that like you can either say aloud or like send to a language model. But there are like a huge number of possible concepts that like the pre-training data that we send to language models could possibly leave active. Like there's like all the concepts that could be in like the code data that you send to the language model, or there could be all the concepts in foreign languages, or there could be all the concepts that are present in like completely different contexts to like store random stories and words, such as like kind of marketing websites, let's say, that are explaining how products work. And because there are just like so many possible concepts that like humans can talk about on the internet, and so therefore are like present in the training data, I'm quite interested in this kind of sparsity prior, so rather than like a Gaussian prior, enforcing that only a few features are firing, because just like it feels to me as if language is a kind of domain where there are loads of possible concepts, but in every particular single sentence, there like aren't actually that many kind of like concepts that are like active at that point. That is kind of like maybe a high level philosophical reason or whatever, but I do think this is kind of like been a pretty successful hypothesis. Because like we have been able to do a bunch of stuff with interpretability far better than we had before because of this kind of sparsity assumption. But with that, we're going to move on to the next question from Abbas. Could you clarify the difference between emergent abilities in LLMs and interpretability research? My understanding is that emergent ability focuses on how LLMs. Cool. Unfortunately, Abbas, I'm going to push this one to the end of the talk because I know we are maybe, I'll probably run over to like the hour, but I do want to like get through all the stuff for everyone. I'll definitely come back to your question, Abbas, but I'm not really going to be touching too much on emergence in the talk, so I'm going to push that to the end, but do keep messaging in chat in the off chance that I forget it, but I probably will just come back to that at the end. So yeah, I guess my kind of like final point that I wanted to like get across with the talk was what kind of like the future of kind of both mechanistic interpretability research is that like I'm kind of pushing on at Google DeepMind, and also that I just think is valuable in general. So there's unfortunately very little of this that's kind of maybe publicly out yet, but the kind of thing that I'm interested in is like applying kind of mechanistic interpretability and maybe specifically sparse autoencoders to kind of actual safety problems. So two that I like bring up here. So this is public work. There's a paper called Refusal in Language Models Mediated by a Single Direction. I wasn't on that paper, but Neil Nanda was, and some like researchers in the mech interpretability space, where they like actually like kind of address like issues where like models like refuse different like kind of requests because they're harmful, and they kind of interpret that this comes down to a single direction in the model. And this is the kind of work that I'm currently quite excited about. And then secondly, I have some upcoming work with some external researchers at METS, in fact, where we're kind of applying the sparse autoencoders to address unlearning knowledge in like language models. So you have like kind of harmful knowledge, such as kind of like the precursor knowledge to kind of like building kind of bioweapons. And we have like some work on like using the sparse autoencoders to unlearn those concepts with mixed results so far. But I guess my point here with this kind of final slide is that I think that in the past, and maybe in the work that I've discussed in this talk, a lot of the focus has been on like understanding the models, like understanding the algorithm, that the model carries out, or understanding like a toy problem so we can try and like reverse engineer how the model works. And while I think that is like a valuable thing to do, and I think that like a bunch of lessons about like how I think about how models work and like how I like do my research on a day-to-day basis is informed by that style of research, kind of blue skies and like kind of foundational research, I think that like it is quite difficult to measure how well different methods are doing when the kind of evaluation is pretty like fuzzy, and just how well do we understand effectively. And so based on that kind of reasoning of the past kind of 6 months and moving towards this kind of future research coming out, I think I'm currently most interested in like addressing actual kind of like AI safety issues, such as like understanding why kind of like the safety training of models fails, or kind of understanding like how we can remove models from knowledge from models, because these tasks can be measured exactly, like whether the model like has indeed forgotten certain facts about like domains, and whether that can be like robustly removed from the model rather than elicited or whatever, as well as like whether the model kind of refuses the correct requests and like or complies with the requests that are like non-harmful. This stuff can be measured, and therefore we can take kind of our like techniques such as like the sparse autoencoders, for example, to see which kind of like features and like concepts are present, and then maybe like improve like how well the models will refuse requests or can unlearn different behavior based on the kind of sparse autoencoder being present. And I think that will give us a good way to evaluate whether the sparse autoencoders are like actually that helpful. And even if they're not, and that will kind of surface like very valuable kind of like different techniques that are powerful for doing these kind of like actual relevant tasks. And my guess is this will lead to kind of more progress in the field, because it's kind of grounded in kind of like an actual evaluation in real life. And so, yeah, I think that's like my current kind of like direction, what I'm like looking to push on, both with these kind of papers kind of outside of DeepMind, and then other kind of work we're working on is kind of like our current direction. But yeah, I think that was all I had like planned officially. So yep, that was kind of like a high-level overview of mechanistic interpretability, where I've come from in doing mech-interp research, as well as some kind of like current and future stuff. So I hope that was helpful, and I'm more than happy to get into some questions. Cheers. Cool. So I'll come back to Eunice's. Oh, sorry, it wasn't Eunice. It was Abbas. I apologize. So Abbas mentioned whether I could clarify the difference between emergent abilities in LLMs and interpretability research. Cool. I understand that emergent abilities focus on how LLMs learn to perform tasks they weren't specifically trained for, while interpretability research is more about breaking down LLMs into components like probability circuits or primitive models to analyze how specifically learned. Is that an accurate distinction, or am I misunderstanding the relationship between those two areas? Cool. Yeah, I guess overall I would say that like interpretability research and emergent abilities kind of like papers and stuff like that are somewhat different overall, but there are a few papers who've discussed both. I definitely agree with your description of interpretability. That sounds pretty reasonable to like describe some parts of interpretability. On emergent abilities, I think emergence is a term that means like many different things across kind of like both like science and machine learning in particular. And my understanding of what most emergent abilities stuff focuses on is where like a behavior or a capability of a model isn't present at some kind of like ability level, such as like when the model has like very few parameters, and suddenly is present later on when the model has like a large enough number of parameters, or let's say was trained on a sufficient amount of compute. And there's kind of like, in some sense, like a step change from when like this behavior wasn't present to when it is present. That's like certainly the definition in the Jason Way paper called like emergent abilities in large language models. And this is a bit different from the definition in like science, where it tends to mean like where I mean it's like similar, but like where it's like when something kind of comes out of some like more primitive like form of like kind of like understanding, but then it's more powerful, such as like how like physics is like kind of like a pretty basic like explanation of how the universe works, but then you can have more like higher level kind of explanations of how the universe works, like in terms of like kind of chemistry being like in some sense a subfield of physics, but then it has a bunch of work you can do that like isn't really best described as physics at some point, like it's more kind of like higher level. And so that's my understanding of what emergence means in the context of science, but it doesn't really matter so much for our discussion. My understanding of what emergence means is, yeah, this kind of like step change in abilities, which like I guess it relates to interpretability in that we also want to like, I don't know, interpret stuff that models do. One thing could be emergence. This was certainly maybe the focus of, there's a paper that like Neil Nanda worked on called progress measures for grokking. So there's this behavior where models can suddenly learn to like generalize quite late in like training. I will put that in chat now, and keep this one. That's like the emergence reference. So there's been work that's kind of interpreted how these models have suddenly like generalized to like understand like a task late in training, but there is work that's like interpretability and not related to emergent abilities, and there's also like emergent abilities work that's kind of not related to like interpretability. So it kind of it's a bit like different overall. But yeah, is there any other questions that people have?
So there was a recent work that came out improving dictionary learning with gated sparse autoencoders. Could you talk about it a bit?
Sure, that sounds good. Yeah, so you're totally right. There was a kind of a work that I was working on earlier this year at DeepMind. I'll stop sharing, but share just a Google tab, because that's probably the easiest way to display gated sparse autoencoders. If I share, sorry about the delay, Chrome tab. Yeah, so I'll be able to put in chat, but improving dictionary learning with gated sparse autoencoders is work that like we worked on at kind of like DeepMind, where we like kind of improved the kind of like architecture that was discussed on the slides, which I can send around as well. Unfortunately, I can't share 2 tabs, but we just changed the kind of like architecture of the like, I guess we do have a figure in this paper. Sorry for the delay. We changed the architecture of the SAE slightly. We have a diagram like here, where we were able to get like some improvement in how like accurately the kind of like input to the sparse autoencoder was reconstructed. And I guess the kind of key thing that was done here that was different to the prior work is I mentioned that you train with like an L1 penalty. That's like you train the model to be sparse by kind of enforcing the kind of like the hidden layer, this like after the ReLU in the hidden layer of the SAE. Like after that, there are like not that many kind of like features firing by like summing them up. And this basically leads to a bias where the kind of like norm of the output of the SAE is like lower than the norm of the input to the SAE. And we had one method of fixing it. And this also had the benefit of being just like a Pareto improvement. So I think we have a plot here, basically a Pareto improvement of basically every single site compared to like the baseline SAE. And for what it's worth, I think this paper has now been like obsolete slightly, because we have, and I hope you can see this, we have a second paper where we like made a second improvement to like the gated sparse autoencoders, and there's also some OpenAI work on improving sparse autoencoders as well. So this has been a pretty hot topic over the past year of making these kind of incremental improvements to sparse autoencoders. And yeah, I think that I think maybe understanding the exact technicalities of what this paper did is perhaps less important than the kind of like high level picture of what the sparse autoencoder is. And I'm like personally a bit more interested currently in pushing towards like actually applying these like SAEs to certain tasks. But you're totally right. That was a paper that we worked on this year, and I'm excited about the results. But I think that like this like is like a more an incremental improvement in the SAE kind of literature rather than like something which is like completely revolutionizing what we're doing, if that makes sense. And yeah, unfortunately, the gated one is a bit obsolete compared to the jump ReLU SAE, but that's where we're at. Cool. We have some more questions. So one of the factors, if paired with interpretability, can lead to the AGI breakthrough. I think, I mean, I don't want to speculate too much on AGI. I think it's probably an important topic to think about. It's very unclear whether like interpretability will lead to AGI. I think that's like certainly possible, but like you can think about interpretability in many ways. One of which would be like, well, we have this great understanding of models, we can maybe make them way better, and that could like be something on the breakthrough to AGI. But I think probably from the kind of safety perspective, the more common way of thinking about interpretability is like as we build more and more powerful systems, which will happen kind of like just kind of naturally as we pour kind of more compute and we make improvements to kind of algorithmic efficiency and stuff into these models, then the hope is that interpretability will be useful to understand the kind of like new capabilities of models and ensure there aren't kind of like dangerous properties with these models that we like didn't like know existed before effectively. But yeah, I guess my overall take is that like I think it's possible that interpretability will be some part of like the breakthrough to AGI, but I would more see interpretability as a method to like help us as like we like scale towards AGI at some point in the future, rather than like the kind of like key driver of progress. But cool. Next question from Christy. Really cool to follow the development of techniques like the AP and SAEs. Is there anything missing from this MI toolbox? That's a good question. So like we have these kind of like current methods of like interacting with or like interpreting the models. What are we missing? I think some things that come to mind here is we still don't have a single fully automated like pipeline for doing our experiments. Like we have a bunch of like kind of like disconnected pieces of research, as maybe I mentioned. Like there's like some stuff where there was like the kind of like AC/DC style stuff, and some people have done that with SEs, etc. And there's also some stuff with like OpenAI's kind of like automated interpretability and labeling the different parts of like models. But there haven't been too many attempts that just kind of like try to like do every part of like the interpretability process or whatever. And it seems that like as the models get better and like they can do more stuff like run your code or like test hypotheses, I think that like automated interpretability pipelines, as in like full kind of like steps that like could be taken from like basically no understanding of like something the model does to like a pretty great understanding of the model, what the model does, will be another thing that would be nice to have in an interpretability toolbox. Yeah, I think that that's the one thing that comes to mind. But it isn't like the only thing as well. I think that, is there any other big things that we miss as well? I guess maybe something that's also worth pointing out here is that like interpretability is like a difficult because of that fact that was mentioned, that often you can't like have a number which describes how well like your approach is working. And so often papers will come out and say like this prior paper had like an interpretability illusion. And so interpretability illusion is like a common thing people have used now. And so like there's a paper which is called like an interpretability illusion for subspace activation patching, and they basically point at a previous paper and go like, we applied this task and like it didn't actually give the kind of like results that they were claiming. And that wasn't because the authors of the prior work were being misleading or like lying. It was more just like it's quite hard to give like interpretations of networks which work like across all cases without having kind of like flaws in them. And so I have some sense that like it might be better if we had some better ways of like evaluating claims about like neural networks and evaluating claims about interpretability, because otherwise we're in the space where we kind of mostly believe what people are doing, but like we're not certain about it, and it's difficult to have a clear standard for what kind of like a good enough research that like actually explains something in models is doing. Oh, and I guess another point here maybe I hadn't mentioned is that like there are like limited cases where like interpretability is used in like deployment of very large models. And so like with very large models, like in like Google with like Gemini and like other like labs with their frontier models, like there are huge kind of like resources put into like the frontier models, but it's difficult to apply the technique that everyone wants kind of applied to those like models. And so it's kind of like less kind of like a big breakthrough with models, but it would be great if we had more kind of like simple kind of like things we could tack on to the models to actually apply our interpretability techniques in practice, such as like the steering vectors and stuff like that. It's like difficult to apply that in practice because it's quite different to what people do usually. And so I think that like if like there can be methods that are kind of very simple and give us interpretations of networks that work on even the biggest production models, that would be pretty awesome for a variety of reasons, like monitoring what the model's doing, as well as like kind of like steering it towards different outputs. But yeah, thanks for the question. I like that one. Abbas says, can we use interpretability research models to find an explanation for ICL abilities in context learning? Like an LLM hasn't specifically been trained to translate through languages and learns to do it by specific prompts. And it's a paper. Cool. I'll check that paper out at a different time. But yeah, I think so. In context learning, this is something which is like a really popular topic, and like a number of people have tried to like explain with interpretability. I think that it's definitely not like a closed like induction heads, transform circuits. It's definitely not like a closed field where we just know exactly what's happening, but there are definitely some like clear connections people have found in mechanistic interpretability between parts of models, namely these kind of induction attention heads and in context learning. And this gives you some explanation at like a very high level where like there's some loss curve here. They show that like, when you have a one layer model, the loss doesn't go down that much, or sorry, the the like in context score doesn't go down that much. Then as soon as you have 2 layers, which is like necessary for these induction heads, we see a sudden like massive kind of like drop in the score, and this corresponds to like a phase change where the model like does learn to do in context learning. And this is in a very toy setting, so these are kind of tiny models, like 3 layers is very, very small. And yet like it's like some evidence for like how in context learning is working. I know there are some follow-up works. There's a paper called like the task vectors paper, function vectors paper. There are 2 papers called task vectors in language models and function vectors in language models, and they basically make a similar point that like you can go from like a 5-shot prompt that teaches the model how to do translation, and then get out from like a 5-shot prompt like singular steering vectors that can then be applied in like the 0-shot setting to make the model like immediately translate like the inputs to like Spanish or something, rather than requiring like a 5-shot demonstration of what translation to Spanish looks like, or like a description in words of what like translation to Spanish is. And so so I'll put that in chat as well, the last 2 links. Then I'll put the induction heads one there as well. Induction heads transform circuits. So like there's 2 links there, but there are definitely some works that are trying to do in context learning understanding. Next question. Irtiza says, sorry about the name pronunciation. Hi, for someone who wants to break into research for Mechanistic, is there anything else except ARENA curriculum and maths research? There's like definitely far more than just like ARENA and like maths stuff, although of course I do recommend both. But I think that like a bunch of professors in academia are like pretty interested in doing kind of like in mechanistic interpretability research, or just generally understanding the models better, particularly because like it's one type of research that doesn't require big models. I think that like we should do like more stuff to be able to like scale interpretability, yet you don't need it to be able to do this research. So for example, the paper on screen right now, it's like David Bao, who's a professor at Northeastern University, and he's like supervises a ton of kind of mechanistic interpretability research. And like the Max Tegmark lab at MIT is pretty into it. And there are a number of professors, some of them don't really call it mechanistic interpretability, but often there are professors who basically do work to understand how the models work inside. And that's a good way to get into mechanistic interpretability. There's also, there are various other programs that will do some amount of Mechainterpret, some part of them. I've seen some research that's been done with what's called laser labs. I'm not affiliated with them, but they maybe post some blog posts and papers that do kind of like interpretability research programs with someone as a mentor. There are like definitely further opportunities beyond that. And you also asked, there was an attempt to automate Mechainterp. And I think I like the Eleuther AI blog. That's another method of doing autointerp, and thanks for sharing the link. I do still think that like that's not addressing, I think the thing I was mentioning at the time probably, of like automating the full pipeline of like every step of like kind of like going from like having a task where you just don't understand what's happening to like an understanding of how the model does it, because it's just basically doing the labeling part of like, here are all the SE features and here's like a natural language description of what they do, rather than like figuring out which of those are important. But it's definitely a nice step forward, and I like that work. And then Adharsh asks, are there any works on finding circuits that are responsible for hallucinations and doing causal interventions done to mitigate hallucination? Any thoughts on this? Yes, there's upcoming research. I'm not part of it, but there's Neil Nanda and 2 of the people he's working with at MATS have some work on finding circuits responsible for hallucinations. There are a number of papers on arXiv as well that have tried this as well. I think, I guess some like hallucinations are interesting. I guess my like thoughts about them are that like they're like somewhat similar to kind of like safety training, where you want the model to like refuse stuff, because you sometimes want the model to say like, I don't know the answer to that, or whatever. You want them to say like, I don't know the answer to that, rather than make up some nonsense or whatever. But they kind of work differently from safety training, because safety training tends to be like the model refuses too much overall. Like it will like, because it's quite dangerous if the model says certain harmful things, like companies will generally try to make the model refuse a lot on like the harmful stuff. But like if on the converse side, you're like trying to reduce hallucinations, and your model just tends to always say, I don't know that, and never even goes ahead with like kind of like trying to produce a response. This turns out to be a very bad experience, because like often you'll eventually get the model to be able to say something, but it'll often have these kind of false positives, or it'll be like, I don't know that, or whatever. And so in some sense, all the models like refuse too little or like not sure this quite called refuse, but it's like say that they don't know what's happening on like kind of hallucination, which makes it a bit of a different task than the refusal work. But I do think it's actually pretty similar overall to that refusal work, like the one mentioned of like refusal is mediated by a single direction. But then Adharsh also says, also if there are work similar to refusal ablation. Sorry, I didn't even read your second message, but you're totally right. And yeah, it's pretty similar to that. And hopefully that was a helpful summary of like the differences, that it maybe happens less frequently, but they're definitely like very closely related. But yeah, I think thanks all for the questions. That's all of them. But yeah, that was really good fun. Thanks so much.
Yes, thank you so much, Arthur, for all your time. Just one last question, if you have time. Could you give like some small project ideas in the field of interpretability for our next phase, like those who can have less compute demands? Can you have like some ideas?
Yeah, I definitely there are a bunch of projects you can do with the GemmaScope 2B SAEs. So Gemma 2B is not that large a model, and I think for a bunch of prior mechanistic interpretability kind of circuits papers, you could like try and understand how those circuits work with like this kind of like like kind of SAE applied to them, which would be like a somewhat exciting project. So to give an example there's maybe, let's say, I have a tab open, yeah, let's say fact-finding Neolander. As like one example, there are some like prior circuits work that try and reverse engineer, say, like factual recall or something, but none of this work actually used SAEs. So you could try and like see whether you can get this working with like a sparse autoencoder, and whether it gives you better progress than this post did, because this like actually didn't have like too much progress on exactly how the facts were stored in models. Beyond just the SAE based stuff with like the Gemma 2B model, I think there are a bunch of projects. Yeah, activation steering is a good one, where like there's this technique, as mentioned several times, where you can try and like add something into a model and make its rollout generally do something different. And I guess some things there that are interesting are like basically improving the reliability of the technique, where often like it won't always actually steer the model toward the output, or it'll make the model kind of very kind of like unhinged and just like a break essentially. And so maybe some like there's a recent paper that tried to do some like conditional addition of like the steering vector, like only added it sometimes. And you can imagine like maybe methods would like adaptively add different amounts of steering vectors. So you could take a look at like kind of the existing literature there and see if there's something you can improve about the kind of quality of the kind of like steered outputs. And yeah, anything else come to mind? If you'd rather not touch kind of like larger models, because, or like larger model where that means 2B, because that's where like the model kind of get interesting with Gemma 2B. There are a bunch of stuff that GPT-2 small does, like the IOI circuit, where you can probably come up with some like a task that GPT-2 small does and try and understand how it does it that way. And beyond just the IOI paper, there's like a greater than paper archive, which again could be done with SAEs actually, because there are like some GPT-2 small SAEs out there as well. But this is another example of kind of like a circuits paper up in the chat. Oops, they're in the chat now. That like tries to reverse engineer something that GPT-2 small does, and that's considerably smaller than like Gemma 2B, and obviously way smaller, kind of like Llama 3, 70B and stuff. And so that might be more tractable. But yeah, hopefully that's a bunch of stuff that will be useful.
That's yeah. Wonderful ideas. Yeah, thank you for that. And thank you for being so generous with your time. And you're like a celebrity for us, all interpretability researchers here, because of all your work. So thank you for sharing and giving us an insight about your work and your future work also. So yeah, I guess thank you for your time, and hopefully we'll get back to you with some interesting project results.
Awesome. Yeah, I'll put my email in chat, which anyone can contact.
Awesome.
I can't guarantee being super fast to respond, but feel free to nag me if it's been like a week or something. And yeah, I'm looking forward to hearing about the kind of projects you guys do, and hopefully that was helpful. But yeah.
Yes. Thank you so much. Thank you for your time.
Cool. I'm gonna head to see you guys.
Yes. See you. Bye.